Okay, so now we're going to go ahead and we've looked at the chi-squared goodness of fit test. So we were looking at really just one variable and breaking up the distribution on one variable. Now we're doing the chi-squared test for homogeneity and the chi-squared test for independence. And remember how I said earlier that they're really the same test, the only difference is how we sample data. And so with these ones, we're going to break down two variables. And so we're going to be looking at what influences what. So we're going to be looking at explanatory versus a response variable. And we are going to compare the conditional distributions of the response variable for each explanatory variable. So if we wanted to know if gender affects favorite color, then I'm going to break down the favorite colors for females, and I'm going to break down the favorite colors for males, and we're going to compare those. Now, that means we're calculating those conditional distributions. So conditional meaning I'm looking at the breakdown for females, the breakdown for males. A lot of times we will graph them to see if there's truly a difference before we even test. Because if we graph and we can see that, hey, there's really a difference, then we can continue. And if we graph them, we're like, no, there's not really a difference, then we won't continue. And that way we can see where the differences are occurring. And then we're going to test to see, are those differences really significant differences, or do they just happen by chance? Now, if there are differences, we are then going to analyze what differs and by how much. So that's our follow-up. So in our test, we're going to do something called, we're going to look at those expected counts, but now it's a little different for our expected counts. So we'll look at the distribution. So if you're looking at favorite colors between males and females, then to calculate expected counts, I'm going to look at the total proportion for each color when I pool the males and females together. And that tells me how much I should expect if there's truly no difference between males and females. And then once I have that proportion to get the count, I multiply that by the total number of females, and that'll tell me my expected values for females. And then I take those proportions and I multiply by the total number for males, and that will tell me my expected value for males. Now for our chi-squared statistic, our degrees of freedom is a little different because now we're looking at two variables. So I'm going to look at variable 1, the number of categories, and -1. Now I'm going to look at variable 2, the number of categories, and -1. So usually we end up with tables of data, and so I take the number of rows, -1, and the number of columns, -1, and I multiply them together. Now keep in mind the test for homogeneity right here means that I'm taking 2 or more samples. So I take a sample of males, and then I take a separate sample of females, and I'm comparing that data. Okay, so again, the chi-squared test for homogeneity. We started off by saying we want to perform a chi-squared test of homogeneity. We put in our significance level. Our null and alternative hypotheses are really nice for these tests. So the null is there is no difference in the distribution of favorite colors for gender. And our alternative would be there is a difference for the distribution of favorite colors for gender. So usually distribution of our response variable would go here. For our explanatory variable. So we're looking how the response differs for each explanatory variable or explanatory category. We then check our conditions. We have our normal random condition, either random sample or a random assignment in an experiment. We're going to do our large sample, so our expected values. So we take that as if the distributions are the same, so we're kind of pooling those explanatories together. And that gives us our marginal distribution. And then we times that by the total for each category, and that'll give us those expected values. And then, of course, we have that independent condition. Then we go through and we calculate chi-squared just like before. Observed minus expected squared divided by expected. We have to list out at least the first two terms. The rest of the stuff we can do on our calculator. Then we calculate our p-value with the chi-squared CDF. Our degrees of freedom, I want to highlight this because a lot of people forget the different ways of finding degrees of freedom. So the categories for one variable minus 1 times the categories for the other variable minus 1. And then remember our p-value is the probability of getting a chi-squared statistic if HO is true. And then we go through, we compare it to our significance level. If it's less than our alpha, we reject. If it's not less than our alpha, then we fail to reject. We interpret those results in context. And then we do our follow-up, which is which cells show the largest deviations. So what has the highest component and what direction are those in? Are they higher than we expected or lower than we expected? So, really involved type of problem here. In chapter 1, we had a sample set of data that examined the distribution of superpower preference for a random sample of 200 children from the United Kingdom. And then we asked, do American children have the same preferences? To find out, a random sample of 215 U.S. children was selected. And then we compared the data. So really, we're looking at, are they different between the countries? So this is our explanatory. And this is our response. So we're looking to see if these responses differ between the two countries. So we're going to be looking at the totals for our explanatory variable to help us out. So right away, we're going to go ahead and work on graphing this. And why are we graphing this with percentage instead of counts? Well, because they have different totals, and the totals are pretty close, so you can still kind of judge that. But because they have different totals, it's hard to say, like let's say this one was 400, and I'm comparing to 215. If I'm only comparing the numbers, it's hard to tell because the United Kingdom would definitely have more numbers altogether. So I can't really say, well, the United Kingdom has more kids that choose fly. Yeah, but you also had more kids in the United Kingdom that you picked from. So we calculate those proportions. So here I'm going to do 54 out of 200 kids chose to fly. And that gives me a proportion of 0.27. And then here for freeze time, 52 out of 200 chose a freeze time superpower, and that's 0.26. And then for invisibility, 30 out of 200, which is 0.15. And then 20 out of 200, which is 0.10, and 44 out of 200, that is 0.22. And so we're going to compare those over here with the United States. So this is going to be 45 out of 215. And so that's going to be 0.21. And then 44 out of 215, which is 0.20. And then 37 out of 215, which is 0.17. And then 23 out of 215, which is 0.11. And then 66 out of 215, which is 0.31. And so we can graph these and we can look, is there really a difference? Are they pretty close? And in fact, we can do that just by telling the numbers. But usually when we're presenting this information to other people, we want them to take a look because the visual makes so much more sense than the numerical. So we're going to go ahead and we're going to graph the U.S. For fly, it's 21%. So right about here. I'm going to do all the US's first so I can use my same color. And then we had 20%. And then we had 17%. And then we had 11%. Yeah, that looks like about 11. See, that's 10. Oh, this is 11. And then for 0.31. So 31. Okay, now I'm going to go back to that blue color for the UK, so 0.27. So you can definitely tell there's a difference there. For freeze, 0.20. Oh, 0.26, sorry. And then for invisibility, 0.15. So pretty close, not a lot of difference. 0.10. And then 0.22. So it looks like our biggest differences seem to happen in the last two categories, the flying and the telepathy. Definitely a lot more on the telepathy than the flying by looking at just the numbers, but those look like where we actually have a difference. So let's actually test to see, is there a difference? So before I test to see, the first thing I'm going to do is I'm going to figure out what do we expect those proportions to be. So I'm going to do an expected proportion, which means I'm going to pool together the information. So I'm pulling together, I'm not breaking it down by the explanatory, I'm looking at these totals. So here I'm looking at 99 out of 415, and that gives me that I'd expect both categories to be about at 0.24. And then the 96 out of 415. So I'd expect both categories to be about 0.23. And then a 67 out of 415. So I'd expect both categories to be right around. So if there's truly no difference, this is the expected proportion that we would have. So 43 divided by 415, which is 0.10. And then 110 divided by 415, which is about 0.27. So when I want to calculate the expected values for each, what I'm going to do is when I'm looking at UK, I'm going to take this 0.24 and I'm going to times by 200. And that's going to tell me the number that I want. And that's what I'm going to compare with this 54. So I would take 0.24 times 200, and that would tell me 48. So these are the numbers that I would be comparing. This is what I actually got. This is what I would expect to get. And then I would take the 52 and I'd compare it to the 0.23 times the 200. And that gives me 46. And so I'd look and I'd try comparing those values to see, is there really the difference there? Or does it just look like there's a difference and it's not really, that could just happen by chance. So, do these data provide convincing evidence of the distribution of superpower preference differs among the United States and the United Kingdom children? So we want to perform a chi-squared test for homogeneity at 0.05. So our null hypothesis is there is no difference between the superpowers for kids from the UK and from the US. And our alternative is there is a difference in the distribution of superpowers for kids from the UK and kids from the US. So check the conditions. Well, we had a simple random sample of 200 kids from UK and a simple random sample of 215 kids from the US. So now we're going to check that large sample. So what I'm going to do is I'm going to take those marginal distributions. So for flying, we expected 24% in each category. So 24% times 200 tells me that for the UK, I would expect those 48 kids. And that is definitely greater than or equal to 5, so I'm good. So now I'm going to take the next one, 0.23, and I'm going to times by 200 kids to figure out how many I would have. So remember, this 0.24 and 0.23, that is these values that I'm grabbing right here. So I'm using these from this value, that pooled data, to help me figure out what I would expect them to be. So 0.23 times 200, 0.16 times 200, and 0.10 times 200, and 0.27 times 200. And so I'm checking to make sure that all of these are greater than or equal to 5. So when I check this out, I get 48, I get 46, that's good, and then I get 32, that's good, and then I get 20, that's good, and then I would get 54, that's also good. So that's what we would expect to have happen. And now we're going to go ahead and look at the United States. So again, I'm going to take that 0.24, that 0.23, that 0.16, that 0.10, that 0.27. I'm going to times by the total number of kids that we sampled from the US. So 215, 215, and this will tell me how many to expect. And so when I multiply that out, I'm going to get 51.6. That's okay that it's a decimal. Well, that's greater than 5. 49.45. Well, that's greater than or equal to 5. And then 34.4. Well, that's greater than or equal to 5. And you get the idea, but I still need to write this down. So 21.5 is greater than or equal to 5. And then 58.05 is greater than or equal to 5. So again, all of these are checking out, and now we have to go back to our independent, and let's see, it's reasonable to assume more than 2,000 kids in UK, and more than 2,150 kids in the US. Now we're going to go ahead and calculate our chi-squared. So for chi-squared, we're going to go ahead and compare our actual value. So if I go back to that, there we go, here's our chart. So we had 54, and I'm comparing to that expected value of 48. So we had 54 was how many we actually had, but we expected 48. And remember, that's the number we had here. So that over 48. And then I'll take the next one, so I'm going to go back and check. We had 52. So 52 minus the 46. And we just keep on going. And so a lot of times you'll see me write the information down. So I'll have, okay, this may be really 54, this was 52, this was 30, this was 20, and this is 44. And on your paper it's nice because you have that chart right there. And so we'd compare the 54 with the 48, the 52 with the 46, the 30 with the 32. And we'd go through and do that. In fact, on your calculator, you're going to put these numbers in as list 1, and you're going to put these numbers in as list 2. And then you go ahead and do your list 3 to get your chi-squared, and then you're going to find the summation. So when we add all that up, we're going to end up with 6.344 as our chi-squared statistic. Now we're going to calculate that probability. So the probability of getting a chi-squared that is greater than 6.344, we'll do the chi-squared CDF with a lower bound of 6.344, an upper bound of really, really big, and then we're going to calculate that degrees of freedom. So let's think about this. Let's go back and we'll talk about how to do that degrees of freedom. So here we had 1, 2, 3, 4, 5 categories. So for degrees of freedom, I'm going to do 5 minus 1, and I'm going to times that by the other variable. So my other variable was 1, 2 minus 1. So this gives me a degree of freedom of 4 times 1. So our degrees of freedom is 4. So now we're going to go back. Degrees of freedom is 4. It allows us to calculate our probability of 0.1749. So because this 0.1749, I test that with our significance level of 0.05. It is not less than that. So we fail to reject. So now on the next page, since our p-value is not less than 0.05, we fail to reject. The null hypothesis. We do not have convincing evidence that there is really a that there is a difference in those distributions. So that could have just happened by chance. Now, if we look back at our components, our biggest differences happened in telepathy. Now, it wasn't enough of a difference, but that's where we saw our differences really were in telepathy. Those were the biggest values. And with our telepathy, we actually determined that UK is less than expected. And US is more than expected. And again, that could have happened by chance because of the fact that we failed to reject our null hypothesis. So could have happened by chance. Okay, next thing. The chi-squared or the two-sample z-test. When we're dealing with two categorical variables that only have two categories, so when we look at our table of data, we're really going to have a 2x2 table. Then we can use a chi-square test or a two-sample z-test. And what we're going to find is our p-values will be approximately the same. The only differences that may happen may come from some rounding errors from not using exact decimals. So, for example, whoops. Let's blow that up a little bit. There we go. So, for example, in a study reported by the Annals of Emergency Medicine, researchers conducted a randomized, double-blind clinical trial to compare the effects of ibuprofen and acetaminophen that has codeine in it as a pain reliever for children recovering from arm fractures. There were many response variables recorded, including the presence of any adverse effect, like nausea, dizziness, or drowsiness. And the results that we have are right here. Now, this is definitely a 2x2 chart. So we've broken each variable into only two categories. So we have adverse effects, no adverse effects, ibuprofen, acetaminophen. Ibuprofen and acetaminophen are our explanatory variable. And then these effects are our response variable. And is the difference between the two groups statistically significant? Conduct an appropriate chi-square test to find out. So we want to perform a chi-square test for homogeneity at a 0.05 significance level. Our null hypothesis is there is no difference in the proportion of patients that had adverse effects. So again, response variable when taking our explanatory variables, ibuprofen or acetaminophen. Our alternative hypothesis is there is a difference in the proportion of patients that had response variable when taking ibuprofen or acetaminophen. So now we're going to check our conditions. Randomized double-blind clinical trial. So random assignment. of 234 kids. Large sample. So now we've got to check our expected values. So we're going to go ahead and we're going to pretend that there's no explanatory variable. We're going to put it all together. We're pulling it all together into that total. So we expect 93 out of 234 to have adverse effects. And that gives me 0.3974. And then I'd expect 141 out of 234 to have no adverse effects. So that's 0.6026. Now to figure out our expected value for each one, I'm going to take this 0.3974 and I'm going to times by 122, and that'll tell me my expected amount here. And I get 48.5. And then I'm going to take the 0.6026, I'm going to times by the 122, and that's going to tell me my expected value for right here. So 73.5. And then I'm going to go ahead and I'm going to take this value and I'm going to times by my 112. So that'll tell me how many I would expect right here, which is about 44.5. And then I'm going to take this and I'm going to times by my total to figure out my expected value right here, 67.5. And again, I like writing those expected values right next to my actual values. So when I do my chi-squared later on, I'm good to go. And so because I showed my work up here, right down here, I can just go ahead and say, okay, 48.5, well, that's greater than or equal to 5, so I'm good. 73.5, yep, that's greater than or equal to 5, so I'm good. 44.5, yep, greater than or equal to 5, I'm good. And then 67.5, yep, greater than or equal to 5, so I'm good. So we've met that large sample condition, kind of like our normal condition for everything else. And now we're going to check independence. So random assignment. Assures independence. And because we're a little worried how one kid might affect another and stuff like that, we are now looking at that double-blind clinical trial. So double-blind keeps other things from affecting it. So it keeps our independence. Because we're looking at cause and effect with our experiments, it's always a good idea to minimize as much of the effect of those other variables as possible, so that double blind really keeps our data independent from each other. And then we're up to our do part. So our chi-squared would be equal to, okay, I'm going to take that 36, I'm going to subtract the expected 48.5, I'm going to square it and divide by 48.5. And then I'm going to take the next value, 86, I'm going to subtract 73.5, square it, and divide by that 73.5. And then I'm going to keep going. And I'm going to do the rest on my calculator, because now we get the idea how is it set up. We make sure we're doing that right, and we get a chi-squared value of 11.15. So now we're ready to go ahead, and we're ready to calculate our p-value. So p-value of having a chi-squared greater than 11.15 is calculated by our chi-squared CDF with a lower bound of 11.15, an upper bound of just a really big number, and degrees of freedom. So what is our degrees of freedom? Well, we have 2 and I minus 1. So degrees of freedom is 2 minus 1 times 1, 2 minus 1. So this gives me 1 times 1, which is just 1. So our degree of freedom is 1. So now we plug that in the calculator. I'm getting 8.4 e to the negative 4. So this is really 0.12384, 1, 2, 3 zeros, and then 84. So when I compare that, is it less than 0.05? Oh yeah, it's definitely less than 0.05. So since it's less than 0.05, we reject our null hypothesis. And we do have convincing evidence that there is a difference in the proportion of patients that had adverse effects when taking ibuprofen or acetaminophen plus codeine. So now what we're going to do is we're going to take a look at if we were to do a z-test. Now luckily, because we did all of our stuff for the chi-squared, we don't have to go through all the conditions. We're just going to calculate it. So we're going to calculate a two-sample z-statistic and the p-value. So we're going to use this as pi for proportion that had effects with ibuprofen, and this is going to be pa for the proportion that had effects with acetaminophen. So 36 out of 122 kids had adverse effects with ibuprofen, which is 0.295. The probability of adverse effects with acetaminophen is 57 out of 112, which is 0.509. And then again, this is z-statistic or z-test, so we pool together our data, and that is 93 out of 234, which means that together, if there was truly no difference, those proportions should be about 0.397. So now we calculate that z-statistic. So I look at the differences between the two, and then I'm going to do my standard deviation, which is pooled. So 0.397 times 0.603 over my first sample size plus 0.397 times 0.603 divided by my second sample size, which gives us a value of negative 0.214 over 0.064, which gives us a z-value of negative 3.34. So now we calculate the probability of getting that or lower, but because this is really either way, we're going to do a 2 normal CDF because it's a not equal to. Because this is negative, my lower bound is going to be just really low. My upper bound is going to be my statistic value. My mean is 0, my standard deviation is 1. And why did I use normal CDF? Well, because it's a z-value, we're dealing with proportions. And then this gives us a 0.000, hey, 3 zeros and an 8, 2665, pretty much the same value that we had before. So same results, same idea. And so now you're starting to see crossover on where you can use the same test.